Thank you very much for welcoming me again. Just quick show of hands, I guess, who uses Datadog day to day? All right, all right, there's one person, so there's a lot of people to convince. No, yeah, exactly. So, who knows about us? So a few more. It's great. So I'll give you a little bit of a sort of a quick run through what we do, so that it'll anchor discussion a little bit. So my name is Alexis. I'm the co-founder and CTO of Datadog, and what we do is monitoring. And so that's why it's obviously a topic I know very well. I'll have to look at my watch because the countdown hasn't started. Okay, cool. So monitoring of applications of infrastructure. So we've been doing that for about 5 years. So it's sort of as I was invited back, I wanted to think about how data has transformed our industry, and by our industry I mean software development and sort of operations. So hence the title, sort of from monitoring to analytics to understanding. So in 3 slides, what we do is really relatively simple. The first thing is we collect performance metrics from a lot of different sources. And in this case, because we're talking about software engineering and then sort of IT and infrastructure, we're talking about sort of web servers, containers, infrastructure as a service, configuration managers, databases, and so on and so forth. So the idea is that you connect Datadog to all your stack, and then we pull in real time data into Datadog. So the question then is, well, what do we do with that after that? So we could do a couple of things. The main thing is to visualize, and this is actually in maybe this is 1890 for the astronomers, but the reality is for the kind of data that we're collecting, which is essentially time series data coming from a lot of places in the software stack. A nice way to present them is dashboards, and that's because the brain, just as you can imagine, is really good at picking up particular patterns, changes in shape, changes in colors, relative sizes, and so on and so forth. So that's a key part of the experience of Datadog, is to actually visualize things. And you'd be surprised to some extent how much that is, I wouldn't say novel, but this is like an aha moment for a lot of the industry. Not the sort of advanced customer of ours, say Airbnb or Twitter or Spotify, but the vast majority of the industry is still kind of struggling with that. How do I visualize the data that I have? So once you can put it on a screen, it's great, but you're not going to watch this for an entire day or even a few hours, because A, you'll get tired of it. B, your brain will sort of things will become blurry, and you'll lose your effectiveness at detecting interesting patterns. So the third thing we built is sort of alerting, and that's basically an engine that watches in real time time series and tells you, hey, there's a problem here. So that's the sort of triumvirate of monitoring. You aggregate all the data, you can visualize it, and you alert on it. Click. Okay, cool. Did I skip one? No. Well. So before it goes a little bit too fast for me. I don't know where I'm supposed to. All right, there. Yeah, no. All right. Okay, so maybe I can wave for. Could you just, I think, rewind one, and another one. Did I skip one? Okay, so. All right, so low tech. We're gonna go low tech. So the yeah, exactly, right. So the reality is that. For the system that aggregates data, visualizes it, for all the customers, the understanding that they have of their application is only as good as their monitoring. And that's because when you think about, I don't know, you use Twitter. So you can imagine people at Twitter, there's not much. They can go into the data center, they can stare at the machines, but that doesn't really tell them how the application is doing, as a whole. They can log in and see and tweet and see how it feels, but that's only going to give them a feel for how the application is performing. So the understanding that people who write software for a living or operate software for a living, it's the understanding that they have of how well the application is performing is only as good as the monitoring, and that's a key point. So that's why we've sort of at this critical juncture as a company. Now, that's there has been a massive increase in sort of in terms of the volume of monitoring data, and I'll sort of dive into two different axes. But the reason what that changes is the tools that you need to process that data. So one of the reasons why that's happened, why there's a lot more data now that we had, say, 10 years ago, is summarized in this chart. So this is what a hypothetical application stack looked like at, say, 2002, up to 2002. So you have bare metal, you install an OS on it, and then you have a database or application server, and you write your application, and that's your stack. And you may have a few of these, but that's it. So early 2002, 2004, something like that. Really, virtualization takes off. It's completely commoditized, and you have multi-core machines. So now you can have same piece of hardware, you just slice it in multiple machines. So now, from a monitoring standpoint, when you think about what you have to watch in order to understand how the application is doing, that you don't have one per piece of hardware, you have multiple. Maybe it's 5, maybe it's 2, 5, or 10. But that sort of increases, so nominally the amount of data that you're collecting by 2, 5, or 10. And most recently, so that's 2005-ish, most recently in 2015, there's further slicing of the infrastructure in that you take the same piece of hardware, and of course now it's much faster, much more powerful. You install VMs on it, and then you sort of turn your applications into microservices. So you use containers. I don't know if people have heard of Docker. I'm assuming you have. All right. So the idea that you sort of create similarly virtual machines inside machines, which gives you a lot of flexibility and is a lot easier to deploy. But you have per sort of virtual machine you can install easily. I think the average we found is about 4, but anywhere from 4 to 100 containers per virtual machine. And each virtual machine or each physical machine can already host 5 to 10 virtual machines. So you multiply 5 or 10 by 5 or 10, so it's up to 100 times the amount of data that you have to process to be able to understand what the hell the application is doing. So as a result, you're talking about a lot more metrics coming in. And so that gets really overwhelming quickly. I want to say it has probably like 30 to 60 time series, and obviously at that level it's already completely intelligible. You just can't you don't really understand what's going on. I mean, there are sort of some stuff at the top, but that's about it. So that's the volume. It's a lot more data. Now, there's another one which is more insidious. I think that's really our industry is the first one to have that. We're in the industry of software, we pay a premium for rate of change. By that I mean, and it's very different from a physical production line, is the faster the production line changes, the better off we are. That means the faster you can go to market, the more features you can introduce, you can beat the competition. So that means that to understand how the application is doing, the assumption you had, in the morning, as you sort of come into work, they may be completely wrong by the time it's by lunchtime, because by then there are 3 teams that have released new versions of the software which fundamentally change the way the application behaves. So a lot of more metrics, and it's changing much faster. So the problem that we're facing is, so there's a lot of moving parts. How do we extract signals? And so data we broadly classify. I can classify in 2 ways. One, which you can imagine, I guess, speaking into this in front of this audience, is with sort of what I call signal processing in data science. So that's really applying robust algorithms to process time series. So yes. Okay, this guy. This was an animation. So one of them is to figure out outliers. And so the idea there is you take a bunch of identical processes that are supposed to be sort of based on the same distribution, and then you try to see if there are ones that are deviate from from the rest. So classic example is you have a load balancer, which basically takes a bunch of web traffic. It's supposed to distribute it across a number of web servers. So you'd think about throughput or latency or number of errors, and you'd imagine if it's sort of round robin load balancing, each machine gets its fair share. If you wait long enough, which a couple of minutes, you get a good feel for the distribution of each machine, and you'd expect that distribution, the samples, to look like they're from the same distribution. So conversely, that's the hypothesis you're making. Conversely, you're saying, well, if I can find something that deviates from the norm, as it were, then that's something interesting. That's something I want to monitor. So I don't want to monitor any particular of the time series because there are too many of them, just the volume of data is too large. Rather, I want to find the ones that sort of deviate. So that's classical, what we call outliers. And that's a necessity, of course, as the amount of data is increasing. Another one is anomalies, is you're not looking for sort of deviation in space, as it were, you're looking in time. You'll look at, well, I predict that it'll behave this way, but it changes, it deviates from prediction, so that's an interesting thing to monitor as well. Technical details, we presented some of that at PyData last week, so I'll let it, so you can look PyData and Datadog and you'll find more details. Okay, so that was the sort of the science part. There's another way we can do it, which is sort of not using science, as it were, but really with a better mental model. And so this is really talking to our customers, talking to our users, and trying to educate the industry as a whole, the field as a whole, say, hey, maybe there's another way to think about the problem, one that will lead us to simplify the problem and sort of cut through the noise. So another reference to astronomy. This is Encyclopedia Britannica, first edition, 1777. This is a way you can account for, and I'll speak under your control, I think, so back in the day, I guess, around the ancient Greeks, they'd look at the sky and say, okay, well, here's a model for how the planets move. I don't think they could do the stars at that point. So it's a very complicated model. If you put the Earth at the center, you have all these epicycles, and it's hard. It sort of works, but not really. And so that in a sense, that to me underscores the importance of the model you have of the data you're processing. And so that if you have the wrong model in mind, you're going to spend a lot of time sort of wasting cycles or brain power trying to cut through the problem. Now, I won't be as presumptuous as to think that we have a revolution like that, but what we did is we decided to go back to the basics and say, well, let's look at the kind of data we collect, and is there a simple classification that we can apply, and so that, more importantly, is there a simple classification that our users can apply to cut through the noise and help them. They can still use signal processing, but it'll simplify the problem a lot. So we publish a blog post, anyway, Datadog Monitoring 101, you can look for it. The gist of it is actually surprisingly simple. Is basically you classify from all the data we collect, regardless of the source, regardless of the application that's emitting it, or whether it's a server or virtual machine or container or database and so on and so forth. You can classify them in three broad categories. One is work metrics, such as throughput, success rate, error rate, performance. The other one is resource metrics, utilization, saturation, error, availability, and a bunch of events, which could be changes in general, stuff like that. So the idea is that work metrics measure value that a particular component is producing. Resource is the amount of stuff that you consume to produce value. So work, in the case of a web server, a work metric is, let's say, throughput, how many requests per second. A resource that is consuming typically is network bandwidth, is CPU, and so on. So as it turns out, not all metrics are created equal, and the ones you want to really care about are the work metrics. So in that large volume of metrics, if you already classify in two classes of metrics, work and resource, you can reduce your search space by a lot. So the general process you're doing is looking at your application as a whole, say, well, what's the work there, what's the resource, and then you look at, so the application, I don't know, is a web server, is a is Twitter. They have a bunch of web servers and so on and so forth. So a resource is a web server. Well, you look at the web server, what's the work, what's the resource, and so on and so forth. And so really the goal there is in addition to sort of data science is really starting to focus on metrics that matter. So that's really, if you will, in conclusion, what I'll say is that in order to simplify the problem for our users, we wanted to apply a sort of two-pronged attack. One is data science, and the second one is education. It's worked, I think, fairly well. And so with that, I'll thank you. I'll just, of course, say that we're hiring, and thank you very much.
Great, thank you. Just to make sure I understand, the anomaly detection, so the data science part, that means you basically run machine learning on top of a bunch of...
That's right. So we run statistical process. We run a mix of machine learning, well, what in the old days were probably called statistical processing, signal processing really, around frequencies, around deviation from the median, stuff like that. And then we run the machine learning part, which is more clustering. But yeah, so we run both in trying to identify which supposedly identical processes deviate from the rest of the group, but also for each process, which ones are sort of not behaving the way we thought they would behave based on historical data.
And how quickly does that work? How much do you need to train?
So the good thing is these are don't require any. So in the case of signal processing, it doesn't require any training, but if only, well, it does require training of the user. So we provide them with it's a class of 2 or 3 parameters, and so we've essentially tuned them so that the defaults mostly work. The difficulty with something I didn't really touch on with this problem. So imagine we're talking about monitoring, which means that when we trigger an alert, we ring the phone, whatever the time of day or night it is. So any false positives, our users are like, luckily it doesn't happen too often, but it's just sort of a highly emotional response to our product, especially from the part of the spouses when it's 3 a.m. So we spend, and it's really the hard part about the science part of it is the quality is a really difficult problem. So even if we do which I like to think we're getting close to, but if we do a perfect job, you're just meeting your customer's expectations. So there's a lot of pressure behind that. That's why we invest a lot of time and money to try to figure out, well, how do we crack that?
Sounds like good times. Quick.
It is.
Questions?
You just started to touch on the question I had of precision versus recall.
Yep.
And that is a trade-off that if you dial it back too much so you're not waking your techs up in the middle of the night, you might miss important signals that trigger, that may presage a server going down and so forth. So is that something that you allow or provide tools for the customer to configure that trade-off in some way or assign costs? How does that work?
So that's a great question. Right now, I'd say no. And the reason for that is, so yes, to some extent, but they're surprisingly unsophisticated. Right now, the sort of feedback mechanism is they tell us, hey, tried this, it woke me up, it's wrong. And in some cases, we can see that it's wrong. In a sense, the reason why it's sophisticated and it reasonably works is that so false positives, people will figure out right away that something is wrong. False negatives, they're rare because it means both. So they have a problem. But also, usually there's multiple indicators kind of watching the same thing. So you can miss them on 80% of the indicators. And you may have latency or lag, but you'll catch them on something else, on some other metric. So that's why I would say for us, it's really false positives. That's the enemy. Somehow, you'll find out when something goes wrong. via either our processing, or we have even more, and I haven't really talked about them, really simple threshold-based alerts as well, which are sort of the last recourse. We say, well, if there's no traffic coming to my site, or there's half of it, then I probably have an issue. So this is a combination. Ultimately, it's really a combination of sort of the data science, but also the more naive approach that we found work well.
Great. One more. Data scientist automated it on the iPad. There was like a bunch of one more question. There were like 6 hands before. No,
I scared them.
You scared them. Yes. Oh, one more.
Hi, hopefully I can ask this properly. At some point in the company, do you think about the idea of, and I'm not sure, the inputs that you're getting from the various services and then spitting them back in a very, very valuable way for the customers. Do you know anything about the machines that they're actually using? So my question is there value or potentially to represent, given this set of instances or services that the customer is using, here are the performance characteristics of that, so they can then compare, effectively benchmark by looking at a variety of services?
So we did that in a less benchmarky way, but we looked at, so for Docker, we actually looked at our data set for adoption. And so things we extracted are number of containers on average, or distribution of containers per machine, which I think the average was about 4. Sort of lifetime of a given container. So there's definitely, there's a lot of data, there's a lot of value. So right now it's only being used as in terms of content, but that's very much something that we want to do, is we want to be able to tell you, for you to figure out, well, where do I fit in the curve, sort of distribution of performance. It's a non-trivial problem, as you can imagine, because there's so many variables, but it's something that people, like, you want to know how well am I doing, at least at a high level. So yes, the potential is there. It's not at this point productized.
Cool. Terrific. Well, thank you very much. We appreciate it.
Thanks, Matt.